So good morning in Germany. Now is 6 a.m. 30 and good afternoon in Taiwan. Today is my great pleasure to have my teacher and then my colleague now, Professor Bernold Fiedler from Freie University of Berlin. He will share his thoughts and research work about sensitivity and oscillations in reaction networks. So you will see a lot of big OD system, but he will derive dynamical information from the network only. So we are very curious about his talk. So let's welcome him.
Thank you very much. Thank you very much for your kind invitation. And yeah, so you already heard a talk in the seminar, which I have not heard, so I do not assume any prerequisite knowledge. Excuse me if I double explain some things. So chemical networks are, I mean, from high school, they are something with letters or unpronounceable chemicals and plus signs between them. And then there's arrows between, and something is supposed to react and form something else and so on. Now, from our mathematical point of view, this is a network, okay? So it is, there is a question, you can write this in various ways, and what are the vertices and what are the edges and of this graph, and there is some directedness and so on. So network language should come in somehow. And the question I want to ask is, what can such a network do? I mean, there are huge networks. There are databases with literally hundreds of thousands of networks, and well, hundreds, comparatively small numbers of drawn networks, you know, where we actually think we know how things work. The citric acid cycle from high school, which gives you energy in all your cells, is a famous example of such a network. And the question I want to ask is, suppose we know nothing else, just the network structure. What can we conclude about the dynamics? And specifically, I want to address two issues, namely sensitivity and oscillations. Sensitivity means you change a network by, for example, killing a certain enzyme by genetic modification. So this means in our language, you kill an edge in the network. What happens? Which concentrations of metabolites will go up and which concentrations which will go down, and what are the effects on the network? That is the one part. And if there is time in the end for the second part, I will talk about oscillations, namely a given network. Can there be reaction rates, reaction constants, speeds of reactions, parameters in the network such that you obtain periodic oscillations rather than just equilibrium responses? Because you see, in chemical industry, all our reactions are supposed to run in equilibrium. If things start to oscillate, they run for shelter, they run away, okay? They expect explosion or something. In contrast, practically all processes in biology, from cell oscillations, glycolytic oscillations, to heart, to menstrual cycles and everything oscillates. Now, that's a big difference in paradigm, and we want to explore a little bit of how much of this we as mathematicians can detect from staring at the networks long enough. Okay, so that's for introduction. Now, let me first talk about something called complex balance, which leads to equilibrium solution, convergence to equilibrium, and to stable equilibria. Equilibria is a term used by chemists differently from mathematicians. I use it synonymously to steady states, but equilibrium really means like you have this balance, and it just balances out. It is equally heavy on both sides. That's the meaning of the word equilibrium. Now, I use it as steady state. So what is chemistry to me? Now, do not please show this to your favorite chemist friend, okay? Because I will use a totally wrong reaction to explain my sort of chemistry. We have hydrogen and oxygen, and those react maybe to water. Now, if you look at this, then it doesn't quite balance out because there's one oxygen on the right. So maybe I have to write two H2O water molecules here, 2 times. Let me do this with a different color. 2 times, and then I can accommodate 1 oxygen, and I need 2 hydrogen. Disclaimer. This is not how this reaction works. It is not happening that 2 hydrogen molecules and 1 oxygen molecule dance a triple dance and form 2 water molecules. This is much more complicated, and there's Nobel Prizes going into these questions. But let me, just for illustration, okay, let me augment this by writing 0 times H2O. A chemist would not write that. But there is no water molecule going in. Then there's a water molecule coming out, right? And there is no H2 and no O2. We are somewhat pedantic bookkeeping mathematicians. Okay, so once we have agreed that H2O, H2, and O2 are participants in this reaction, we can call them X1, X2, X3, or up to XM reactants. And the green stuff are the coefficients here. These are called stoichiometric coefficients. So how many molecules of what you need to produce a product, and what gets out of this, okay? So here's on the right side, there is a plus, and there's a plus here. So from our point of view, from our abstract point of view, all that matters is the, oops, wrong color now. See, this is what happens when you use colors. We have a vector, a coefficient vector. The vector is 0, 2, 1 on the left, and arrow is the edge, and the next vertex will be the vector 2, 0, 0. Okay, so this is how we abbreviate this to scare the chemists, okay, because now it's all numbers. And then there's something that is called mass action kinetics here. Mass action kinetics tells you how likely, if such molecules meet and dance around each other, how likely it is for them to form a complex, that is to get close and react and form the product on the right side. And in the simplest case, this should be proportional to the probability of meeting the appropriate number. You see the stoichiometric coefficients as exponents here. X1 squared, for example, no, X1 to the power 0, X2 squared, and X3 to the power 1 here, with a certain reaction rate, which may depend on temperature, etc., but we ignore this for the moment. Okay. So now we have a differential equation, and a differential equation tells us how the concentrations, X1 is the concentration of the chemical X1, and X2, etc., how those change with time. And it is the reaction rate. So this here you have the stoichiometric coefficients, and here you have the scalar rate for each reaction, J. This is a scalar rate. So maybe we can write J here in front. This is the factor which tells us that Y bar J molecules are produced, the coefficients on the right, and Yj without the bar molecules are consumed for this reaction. So this gives us an ordinary differential equation. And from now on, we are in business. We can do math. We can forget what was before, except just like Hamiltonian, just like mechanics leads to very special structures, Hamiltonian systems, symplectic dynamics, and so on. Also, chemical systems lead to a special structure. Namely, we have a coefficient matrix here, a linear matrix, which I should denote in green, the so-called stoichiometric matrix S. That's the collection of these right-hand side minus left-hand side linear coefficients. And then we have a vector of reaction rates, boldface R of X. So this R goes from some Rm to an Re. E is the number of reactions. The edges, the number of edges in our graph. And the stoichiometric matrix S gets us back from Re to Rm. You see the coefficient vectors Yj now play a double role. They are at the same time vertices of a graph with arrows between them, and they are also vectors which enter this matrix S. So this is network here, the green stuff. And the R is nonlinearities and problems, and ordinary differential equations and dynamics. A steady state or equilibrium is a solution which does not depend on time. So we have x dot equals 0, and we get this kind of algebraic equation. All right. So much for the background. And now a special case of equilibria. A special case is when x star is such that complex balance. Yes, question.
So you need a steady state to be positive, right?
Well, yeah.
Okay.
Yeah. I mean, if you want it to be meaningful in chemistry, you want x star positive.
Yes.
Let me note this. And also the reaction rates should be positive for positive entries. Okay. Otherwise, you just omit them. Mm-hmm. If they are always 0, or yeah, they shouldn't become 0 at positive concentrations. Okay. So these are standing assumptions, which I forgot to mention. Thanks, Jaya. Okay, but now a special case of x star is that for each y hat, for each complex, these could be typically many more than components. M of chemicals. But still, if at any node you have like a Kirchhoff law, that means the number of fluxes, the real number of flux rates going into that node equals the number of fluxes coming out of these nodes. If this happens to be equal, you must be lucky. The network must be good, or you must be lucky with the coefficients, because you have too many equations in too few unknowns, okay? But if you have complex balance, then the network gets, so to speak, much stronger, much more important, okay? Let me show you how. If you have complex balance, now I assume complex balance, I assume mass action kinetics, then I can construct a function v of x, which is sometimes called relative entropy. So I use the steady state, which achieves complex balance here. But that's just coefficients, and essentially this is, except for a linear term, this V is an entropy, X log X, okay? And then shear luck strikes. Under mass action and complex balanced steady state, this relative entropy is a Lyapunov function. It goes downhill. It is a decreasing, very abstract energy. This does not always hold. This is not thermodynamics or something, okay? This is a hope. Now, some people, like my good friend Alexander Mielke, they say this is the only physically possible state. But then you can prove global convergence to equilibrium. Let me show you. When you have complex balance, you have ODE Lyapunov function, you have a PDE Lyapunov function. Mielke himself showed you have, even in the PDE, when you have coupled systems, if the coefficient matrix is identity or behaves well with the Hessian of the relative entropy, you have exponential convergence to equilibrium. Borosh-Hofbauer showed that certain concentrations cannot die out under additional conditions, ODE permanence, which is something much sought after in population dynamics. So you have boring dynamics, convergence to equilibrium. What happens to us when we converge to equilibrium? Well, either we fall asleep or we die. Okay, so eventually it is easy to predict what happens to man and woman. We die, ash to ashes, okay, dust to dust. In between, however, that is not the most interesting state which we would like to describe. So where did all the dynamics go? Now, the difference is, of course, that Alexander Mielke and the entropy people, they talk about closed systems. But we eat and have to go to the toilet for exchange, but we are not a closed system. We are fed. We had lunch. We, you know, so we are in non-equilibrium, but we are non-closed systems. So this simplistic thermodynamics does not apply to open systems. So that's why I want to explore both. No oscillations due to Lyapunov functions, but there is a hidden trick here. I said to have complex balance, the assumption which gave us the Lyapunov function, we need to solve these equations. But these are more equations than we have variables for. Therefore, in general, we will not have any complex balance equilibrium. For example, if you have a cycle, so this is something that Wegscheider studied in the beginning of the 20th century. When you have a cycle of reactions, then you can multiply all the reaction rates and cancel the reaction rate coefficients in mass action for the forward and for the backward, because the forward has to equal the backward rate at each point. Okay. And now, if you calculate that, then in order to have an equilibrium, when after multiplication, you can cancel all the concentrations and you get the product of the reaction rates. And this means that the product of the forward reaction rates equals the product of the backwards reaction rate, so that everything cancels out and you have a solution. In general, this will not be the case. In the citric acid cycle, it's a directed cycle. There is not much of a backward reaction. The enzymes are forward working machines in each cell of yours. Okay? So the Wegscheider relations can be derived from thermodynamic principles, but require closed systems. So in general, you cannot assume them to hold. in general, you cannot assume existence of a complex balance. Now, let me now pass to a more general perspective and drop the complex balance and talk about reaction rate and reaction kinetics. You see, there is, on the one hand, the mass action kinetics, which says that the reaction rate here for each reaction is just a product of concentration. Now, if you put this equals 0, you want to look for equilibrium, get a system of algebraic equations. Hooray! All the computer algebra are very excited about it, and they start talking about Gröbner basis, etc., etc., etc. This is very nice. However, mass action is good for gas or for dilute solutions and so on, but it is not good in the body. In the body, we typically have enzyme catalyzed reactions. And one example of those is Michaelis-Menten kinetics. So this is where the reaction rate saturates. When XM gets large, the reaction rate reaches a limit and does not, think of YMJ equals 1, reaches a limit and does not further increase. So what can we do with that? There is a big difference, and the big difference is this coefficient here. Let's look at the reaction rates, Rj, and their partial derivatives, like they enter the Jacobian matrix. If you linearize this, then you have a Jacobian matrix, you have the partial derivatives of Rj. And if you calculate this Rjm here is Rj. I'm out of luck today with my, this Rjm here is Rj times a stoichiometric coefficient. Doesn't like me today. I will not write now. So you have the Rj times the stoichiometric coefficient and divided by a concentration. But remember, you have J and M as variables in the partial derivatives, and you have only an XM here. So this means there is a hidden relation between the Rj and between the partial derivatives. When, however, you study Michaelis-Menten kinetics, you have this additional parameter. And this additional parameter, if you calculate Rjm over Rj, is still present. You are free to choose if you want to study all such networks. And I do. I do want to study all such networks, and I'm free to choose these coefficients. So therefore, I can think of the Rj's, which make things an equilibrium. You see, SR equals 0 is a linear equation in the values Rj. I can consider the values Rj, positive of course, and the partial derivatives, also assume positive, more reactant gives more reaction, to be algebraically independent. And now I'm not talking about the coefficient Kj or Cmj anymore. I'm talking directly about Rj and Rjm as new algebraic variables, which allow me to analyze the systems. And when I talk about all values of Rj, Rjm, then I talk about all possible coefficient values. And this is something that the algebra people have not considered so far. And that's why we get a flurry of new results. The first of these results is the following. So here is our ordinary differential equation, our stoichiometric matrix, which goes from Re to Rm and maps the unit vector to this column vector. And then there is a new object which we call child selection. A child selection is a map from the set of metabolites, 1 to capital M, 2, so this is a set of M integers, okay? The integers from 1 to capital M. And here the reactions, that's the edges in my reaction graph. And it's just a map. And we call it a child selection. So we are saying each metabolite may have various reactions in which it can enter, which it can affect. We call these reactions the children of the mother M. You know, nowadays in gender language, you have to emphasize the female element. So these are mothers of children, okay? And a mother can, of course, have several children. It could have a single child. Okay. Now we overlook the slight problem that in this chemistry parlance or mathematical parlance, only mothers have children together. Okay, so I'm sorry for you guys. There are no fathers anymore. Okay, but this is just for the language of it. So the metabolites, M metabolites become M mothers, and the reactions which they participate in become their children. And a child selection means that each mother picks a child, okay? Picks one favorite child. And then I can look at the columns of my stoichiometric matrix, which consists of those reactions of those children which have been picked by their mothers, by the child selection. And I assume that that determinant is non-zero for some child selection. There exists a child selection where this much smaller determinant is non-zero. Then the Jacobi matrix of this system, SR prime, has non-zero determinant. That's a square matrix again, right? Is it always non-zero? No. This is a huge polynomial. I will show you examples where this contains millions, polynomials of millions of terms, okay, products. But it will be non-zero as a polynomial in the partial derivatives, and the partial derivatives are our new variables. So mostly, when this polynomial does not vanish, mostly the determinant will be non-zero. So this is what I mean by non-zero algebraically, okay? And then Nicola Vasena has much refined this very crude description that I give here. That's the first theorem.
I have a question.
Yes.
Is the theorem if only if theorem or just one direction?
Actually, you are right. It is if and only if. And the reason is that, let me try one last time to write something here, okay? So let me call this matrix capital R, okay? Then the proof is based on a Cauchy-Binet formula, which basically says that the determinant of SR, you see, this is a weird thing because these are rectangle matrices. These are not square matrices. S is much longer than high, and R is much, okay. So it's like this. This is S and this is R. Yeah. Then Cauchy-Binet says this is the sum over the M element. So now I have to say this is M cross E. This is E cross M. So, and now I take the E prime subsets of E. Can you see that? Of size M. And I take det S, and here I take the columns E prime, and I multiply with the rows E prime of R. So I take a subset here to make everything square, And I forgot. And I multiply these determinants.
Hmm.
And you see the set E prime is my J of M. And due to the special structure of R, this is basically, so the terms which come here are products are J of M, M over M, for each J, for each child selection. But here I take the same columns. So I can expand this, and with a sign I get terms. I call this, for simplicity, I call this R to the J. Okay, for obvious reasons. This is a monomial in RJM, and there is a factor then in front, so that SR becomes a sum of stoichiometric of coefficients which come from this determinant, and a plus or minus sign depending on the signature induced by the child selection times R to the J. And this is a monomial. And the sum is over all child selections. This is how the child selections enter into these theorems. And there are more or less complicated ramifications in other settings, okay, which I will not go into. Okay, that was a little fast maybe, but it's just Cauchy-Binet formula, Cauchy-Binet, which you can prove by alternating forms and so on, but I will not go into that. Now, let me talk about sensitivity. So what do I mean by sensitivity? I mean, after half an hour, it's about time I explain at least one of the words in the title. Sensitivity means I slightly change one of the reaction rates. Infinitesimal change. Knockout is the experiment. Knockout is an integration over infinitesimal changes, if you like. But I take an infinitesimal change, and then just by the implicit function theorem, I know, and I have an equation for the partial derivatives of the equilibrium with respect to that change of reaction rate. So if I slightly change reaction rate J star, I get a dj star of x star, which tells me the first order perturbation of the equilibrium. And that is, of course, multiplied with SR prime. That is our Jacobi matrix here. And I also have to differentiate implicitly, implicit function theorem, the R with respect to reaction rate J star. That gives me a Jth unit vector.
Your slide is gone, so
yes, this is what I expected to happen.
Okay, then
it happened many times, and I have to restart. I have to share again.
I see.
I apologize. This happens all the time with WebEx and never with Zoom. So my university chose WebEx, of course.
You are back. You are back. Yes.
I'm back. Okay. So all I did was implicit function theorem. Just a second. No. Stand only come later. Okay. It crashed again. I cannot believe this.
Oh, I see it again.
I hope I'm in the right.
Yes.
Okay. So so here I'm just doing implicit function theorem to determine the change of the equilibrium as I change the reaction rate. Okay, it's an implicit equation, just implicit function theorem. And the partial derivative with respect to a change in a reaction rate, I call the metabolite sensitivity. How sensitive is this thing? How much does it change? For example, it might not change at all. So if I change a reaction, a flow rate somewhere in my network, there may be some concentrations which are not affected by that at all. Nature wants to get some things very, 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 very fixed, you know. And now also I talk about the flux influence, namely I'm saying how much does a change at J star affect at J star of the flow rate? How much does it affect at a different position in my network the flow through that arrow? Okay? This is what I call flux influence. And let me illustrate this with a little movie. So this is Laurel and Hardy, comedians of the 1920s, Great Depression time. And now let's see what these guys are doing. Ah! So the guy on the right tells the fat one to go take a shower. Maybe he smells or something, okay? Now he is going to change flow rates in the bathroom. He opens there, but the flow on the left changes. So he can stop that. Now he opens at the sink, and of course the flow in the bathtub changes. As he reaches down there, the shower starts, and I think you understand that flux influence is a complicated problem, okay? Now he calls a plumber. We cannot do that, okay? We have to do mathematics. And if you have a large network and you don't know who the plumber was, then this is quite a formidable task in large networks to figure out what happens when you push one of the flow rates. So here is the result, jointly with Bernhard Brehm. Consider any non-degenerate steady state in the algebraically non-degenerate way that we studied. Then, algebraically speaking, so as polynomials, non-zero flux influence is transitive. This means if in a large network, I will show examples, if you push the flow at position J star, and it influences, it changes in a non-zero way the flow at J. And if you also know that once you push at J, the flow at J prime changes in a non-zero way, then J prime is also affected directly by pushing at J star. It's pretty much like the Laurel and Hardy movie. Okay. Now, when we were working on this theorem, I was at a frequency of 1 day or sometimes 1 hour, changing between true and false. I couldn't figure it out. At some points, I thought this was entirely obvious, and then I thought this was obviously false. Why should it be entirely obvious? Well, because if this influences that, it changes that. And if you know that when that changes, the third one changes, then of course you have a proof. However, things are not that simple because of collateral damage. When you change here, not only this flow will change, but also lots of other flows. And who tells you that these other flows do not cancel the effect of a change of the middle guy alone onto the final target? Okay. So this is a theorem, and the proof is a little bit longer than I have time today, so I will skip that. And I should say that Nico Vasena much refined these results, and I think he talked about sign flux influence, because the question is not just does this flow have an influence on metabolite or flow rate, such and so? It is also, does it go up or does it go down? In which direction? I mean, you want to know whether the water goes on or off. Huh? And this sign flux influence, if from here to there it's plus, and from there to there it's also plus, the flux influence is not transitive. This is a strong warning that flux transitivity is not a trivial matter. Okay? And Nico figured out how exactly to do that. And you heard some of that. And if you want to understand that deeper, you have to invite him again. Corollaries, simple corollaries to take home. So we observed that, single children have no influence. This is something you can see in life. You have a mother with a single child, only one reaction going out of this metabolite. And the single child goes astray. It does strange things. But whatever that single child in its flow rate might want to do in its coefficient, the mother concentration will compensate exactly for that in any such network. It will automatically compensate, and nothing of the child's behavior will ever be felt by the outside world, by the outside network, I should say. Yeah? Now, Nico further explored that, and he said that twin sisters have opposite influence, something you can also experience at times. So you have a mother with two outgoing reactions, and if the flux rate of one increases, then the other one decreases to compensate the effect of the sister. Okay, so this is another reason to give such family names to the objects that we are talking about here. Let me do experiments here, and here is a 3-carboxylic citric acid cycle, which was studied very carefully by Japanese guys. I'll show you their results in a moment. And on the left, you see such a network. And what is in the upper left is there's sugar going in. And there are nice things coming out. For example, ethanol down here, and other things you might want, or lactate is maybe not what you want in your muscles. And down here you have the citric acid cycle. Okay. Now, if you apply the previous theory to that system, you get the following diagram. You get the feed of the glucose on top, and then the arrows mean flux influence. So if you change the feed of glucose, of course, everything changes in here. But if you change one of these reactions, 2AB, etc., so the orange guys, then it affects the orange guys and everything below. So even though there's cyclicity here, the transitive structure, the transitive influence structure defines a hierarchy in the system. Now, through decades of study and experience, the citric acid cycle and its phosphorylation groups and so on have been studied so carefully that they nowadays draw the network in such a way that intuitively these hierarchies are already present in their pictures. However, we know nothing about this. We just put it on the computer, figure out the influences, and we get this diagram through mathematics alone. So such is the power of structuring these results. So once they give us the network in non-drawn form, presumably we could identify hierarchies here. I have something on what happens when you augment networks, but I will skip this for reasons of time. This is what actual experiments look like. Here they have a table of certain enzymes they changed here, and then they tell us which proteins go up and which go down and are expressed more and less and so on, the measurements in the network. Okay. And blue means something goes down and red means something goes up. And these are for knockout experiments. So they don't do small variations, but big. But if you have a non-zero sign all along, then of course the non-zero sign augments from local to global. So there's a local to global transition here in these theorems, which lets you reach and predict knockout experiments. And so here are some test cases where this actually works. Now, I should say that the experiments are knockout in the sense that they influence a flux, or they kill a flux possibility. They kill an arrow in the reaction diagram. But what is measured is metabolites. The metabolites, however, follow the fluxes. So there is no metabolite transitivity theorem. Metabolites are mathematically the wrong object. The experiments mix metabolites and flow rates. That's why I think this went undetected for so long, this principle of transitive flux influence, because always half of it is hidden in the experiments from the experimenter. But the metabolites, of course, once you know the fluxes, the metabolites follow the fluxes. So we can conclude, I should have said this in these diagrams. So on the top there is the fluxes, and on the bottom is the metabolites which follow from these fluxes. So when these fluxes up there change, then the metabolites in the bottom box also change. But the leading object one should think of is the fluxes in the network and not the concentrations of the metabolites. Okay, fine. Now, in the last 15 minutes, let me try to talk a little bit about oscillations. Here is a list of a few oscillatory chemical reactions. These, let me just look at the early ones. Already 1828, a guy Fechner in electrochemistry noted oscillating chemical processes. This was a problem with early batteries. When Georg Simon Ohm discovered Ohm's law, he didn't know it was Ohm's law because he discovered it, of course. His main problem was not measurement of current or such things. His main problem was to produce a battery with a constant voltage, because there was something called in German Wogen der Kraft, the waviness or the changes in electromotive force, as they called the voltage then. And these changes were actually already signs for oscillations. Okay. And then Volterra-Lotka. Aha.
Yeah, you are out again.
Here I am out again. And I will restart this. Okay, it looks like I'm back.
Yes.
So Volterra-Lotka was not about population dynamics and predator-prey systems or anything like that. Lotka originally designed his system to describe chemical oscillations. Okay, in very dirty chemical reactions. So later they were replaced by others, but he was really a pioneer. And it was Volterra who said, but this also works on populations. Okay. Without knowing, so at first he didn't even know Lotka's work. So Volterra was 7 or 8 years later. So stability and cycles. Let me mention a linear algebra theorem, which I find very interesting. Call a matrix A semi-stable if the real part of the spectrum is less equal 0. So we think of x dot is ax. So this is linear. But now I call it sign semi-stable if any other matrix B of the same signs of each entry, of the same sign pattern. Plus remains plus, minus remains minus, zero remains zero, is also with spectrum in the left half plane. So that's sign semi-stable. And then when I take products of matrix elements, you know, in a cyclic fashion. So I pick P matrix elements where each points to the next row. You know, I have M1, M2, then M2, M3, M3, M4, and so on. I call these P cycle products for obvious reasons. I mean, it's a P cycle, a cycle of length P. Now, the theorem is the following. This is an old theorem of 1969. It's a complete if and only if characterization of semi-stable matrices, sign semi-stable matrices. Namely, the diagonal has to be less equal 0. Any two-cycle products, so you see these guys are symmetrically located. Any two-cycle product has to be less equal 0. And any even longer cycle has to contain a 0. So this is an if and only if characterization where from the signs of a matrix alone you conclude semi-stability. Very nice theorem. We don't tell this to our students because otherwise the proofs of semi-stability would be too easy, right? Now, this tells us if we want instability, if I want Hopf bifurcation, if I want oscillations by Hopf bifurcation, I should look at violations of the sign semi-stable theorem. So I should look at reaction cycles. And for me, reactions, you see, I mean, they are something with arrows. And here are metabolites. And I have already linearized the equation at an equilibrium. And so then the reactions leave off diagonal terms. And diagonal terms, I'm always keeping track of the diagonal terms. And this B0, B1, BP minus 1, I can enumerate them in such a way to form a P cycle. And now, of course, I focus on P cycles because that's the things which Rupert maybe forbid. Okay, they want semi-stability and I want oscillations. So I have to violate their theorem, and I'm going to violate it through such a P cycle. And as a bifurcation parameter, I take a normalized product of the diagonal versus off-diagonal terms, ignoring the signs. Now, autocatalysis is an important thing studied much in chemical oscillations. Autocatalysis means that on the diagonal, the linearization contains a positive term. So the standard would be negative. You consume something in this reaction. You consume XM. But if by consuming XM, you can produce more XM than you consumed, then you get a negative entry on the diagonal. If you produce more than you consumed. So XM acts as a producer of itself. It catalyzes its own production. This happens in biological systems, of course. And I count the autocatalytic elements in my cycle of length P. And then there are certain other signs like the arithmetic mean of the guys on the diagonal or the harmonic mean and the sign of that and so on. But these are numbers plus or minus 1, not so relevant. Let us focus on the cycles. And I call a cycle of length P, like drawn here, I call it oscillatory if a certain quantity is larger than 2. The certain quantity is the autocatalytic guys minus the length of the cycle. So, for example, the extreme cases is that everybody is autocatalytic, then this gives me a number p, or that nobody is autocatalytic, that also gives me a number p. And then there are corrections which are a little bit messy, but they are just numbers plus or minus 1. For example, if p out minus p is 5 or larger than 5, then I call the reaction cycle oscillatory. Why do I call such cycles oscillatory? Because of the following theorem. If I have an oscillatory reaction cycle, then there exist general monotone rate functions like of the Michaelis-Menten type, which experience global Hopf bifurcation in the parameter A. So not just local branches bifurcating from equilibrium a little bit, but global branches with amplitude or parameter or almost minimal period going to infinity. This is a very long story, and I can give another talk on this another time. Let me just tell you today. Yeah. Not next week, okay. So let me just, for today, illustrate how this works in specific cases. I will skip the proof. Well, this is only a pretended proof. And let me do the examples. So in the oreganator example, that's a known oscillatory reaction. I wrote the general form of this here. We find a cycle, a three cycle in blue. Well, obviously, I mean, here's the blue 3 cycle. And then we have diagonal terms which may or may not be autocatalytic. You see, it depends. Think of R21 as being small. It depends on R3 prime, the derivative being larger or smaller than R4 prime, whether or not you have an autocatalytic step here. Okay. And also in the off diagonal, there is a sign choice which you can make here. Accordingly, there are 2 possible 3 cycles for which, through 2 possible parameter regions, sorry, for which the theorem on oscillations applies. Now, that's not a big surprise because, come on, I mean, everybody knew the oreganator was designed to explain oscillations in the Belousov-Jabotinsky system. Okay? But this is just a test. Now, perhaps a little more interesting is the citric acid cycle here with 8 reactants. So this is what we saw in the lower part of the complicated network before. And here we find, according to the theorem, a 3 cycle, which can cause oscillation. We can find a cycle of length 4, which can produce oscillations. And finally, in the mammalian circadian clock, this is the stuff which governs our sleep-wake cycle, our 24-hour cycle. That's a big achievement to have a relatively precise 24-hour cycle in mammals. It's located in the suprachiasmatic nucleus in the brain, and gives us a very slow ticking clock. Typical time scales, cell division and so on, are on the order of minutes, 20 minutes, an hour or so. But these processes are able to stabilize very slow oscillations. And if they don't, then you sleep at strange times and so on. And if you write this in terms of differential equations, I want to convince you that you don't want to read that. Okay. You just don't want to read that. And there are 100 whatever coefficients which you can choose and so on and so forth. Okay. And believe me, most of these are not measured. But studying the possibility for oscillations, not quantitatively what the length of these oscillations is, that is relatively easy. Here you have a green cycle. of length 3, which works. And here on the other side, symmetrically, is another one. So the whole thing has a somewhat symmetric layout. I think that is one design structure to stabilize these oscillations. Here is a 5 cycle in that system. And here's another large 5 cycles involving gene activities. So that's the scripted things. Then messenger RNA, which I left out here, and the proteins encoded, and those proteins get the clock ticking then. Okay, so that's the working machines in the cell. So at least with this glimpse, I want to complete this talk. And here is a summary of topics I at least partially talked about. I thank you very much for your extended attention, and I'm happy to take your questions. Thank you
very much, Professor Fiedler. Thank you for this very deep and nice talk. So any questions, comments, remarks from the audience, please just unmute your microphone and just ask.
Professor Fiedler, thank you very much for your interesting talk. Here I have a small question about your global Hoffification result. I think it's theorem 4.
Wow. I wish I had half your memory.
You have too many theories. Okay, here.
It's actually, yeah, it should be, yeah, the numbering 4 is probably wrong, yeah. Anyway,
Anyway, so my question is, it's quite complicated for me. So how do you know the A you choose would be the good choice to be the parameter, verification parameters?
Yes.
I think your A is quite complicated.
Yes.
Yes. So let me at least mention what I'm doing here, okay? So you see, first of all, when I linearize, so this equation is like already linearized at an equilibrium. Okay? But then the problem in this theorem is I have almost no assumptions, right? So, and then I have to pick the parameter. The first thing I do is I say, suppose there exists this cycle, the blue cycle, violating the wonderful matrix theorem, okay? Violating, so this is non-zero. These are non-zero entries. And then there are some diagonal terms. And then I say, okay, let us assume these diagonal terms are also non-zero. So either these guys decay or are used, or maybe they produce themselves, but I don't care. Whether sign is details, okay? Then I make these coefficients in the big matrix. I make these large. And I choose all other coefficients small. So all others are already near saturation or something like that of the Michaelis-Menten. So this means that a substantial, the relevant part of the spectrum is confined to such a matrix, and all the remaining spectrum is small. Maybe stable or unstable, or I don't talk about that anymore. Fixed, okay? Remaining spectrum is fixed. And this is the large guys. So I have to do perturbations of matrices a little bit. And this is a cyclic monotone feedback system, as Hal Smith, Malipare, and John Malipare, George Sell, and others have studied. As a side remark, or also Valdiero-Oliva, it fits in the Jacobi tridiagonal systems and so on. And the spectrum of this is well understood. For example, real parts, so there can be real parts of complex pairs, and there can be real eigenvalues, but they are all ordered in pairs, basically. So there may be a first most unstable one, then comes a pair, then comes a pair, then comes a pair, and between pairs there are gaps and so on and so forth. So this is related to nodal properties and so on. But when I saw this Quirky-Rupert maybe theorem, I saw, of course, this fits with the cycles that these other guys studied. But now, for simplicity, let me look at this matrix alone, because that's where all the music is, where the oscillations are for local bifurcation. Local, okay, not global. Okay, what's the characteristic polynomial? It's very easy. It is the product of the lambda plus the a's, but the a's have been scaled. I mean, I pull out a scale factor here to get my parameter. And this is what I choose as a parameter. And the alpha m's are the relative size of these diagonal terms with signs, okay? The alpha m's are az. So alpha m is am divided by a. Very easy. And then I get this off-diagonal flash here. This is the b, scale b. Okay. So this is my characteristic polynomial. Very easy. And now I study that characteristic polynomial for two extreme values. Namely, well, a should be positive. It was an absolute value of something. So a could be 0 or infinity. What happens when a equals 0? Well, I get lambda to the length of the cycle, p, that's the size of this matrix, minus b. What happens if a tends to infinity? Then this polynomial behaves like this product. The b is relatively small. I can put b equals 0. So here I know all the zeros. Very easy. Lambda divided by alpha m minus. And here I get roots of unity. Also very easy. And now I have a few cases. A equals 0 is on the left here. And a equals infinity is easy because you see the positive alpha m's, the positive a's here, the usual case gives me negative eigenvalues, and the autocatalytic ones give instability. Oh, the chemists somehow always knew that, you know, that autocatalysis generates some sort of instability. So I know the spectrum at A equals infinity, and I know the spectrum at A equals 0 from these roots of unity. And there is a period 4 in the precise arrangement of these roots of unity, but this is all for kids, you know. I mean, this is you can give this to your first year students to figure out what these things are. Now, I keep the reaction rates fixed. I only change the derivative, the partial derivatives. That was my trick of saying that the reaction rates and their derivatives are algebraically independent quantities. So I can change this matrix without changing the equilibrium. I have an equilibrium all through A. The reaction rates stay constant, stay the same. And now I linearize. Now along this equilibrium, horizontal is the parameter now. Now I'm doing bifurcation analysis, okay? So this configuration, one of these configurations must become that one. Now I have to watch the eigenvalue 0, but an eigenvalue 0 of this matrix is, as it appears with A, is a relatively easy task to figure out, okay? To get an eigenvalue 0, you just put this equals 0. I mean, it's you put lambda equals 0, and that's really trivial, okay? I mean, this means A equals 1. Can be under certain sign conditions, A equals 1 will have an eigenvalue 0, okay? But forget about eigenvalue 0. Once I have dealt with eigenvalue 0, the only passage from here to here is by such guys crossing the imaginary axis. That's hopeful. Now I can do cyclic monotone feedback systems and so on, and prove transversality, blah, blah, blah. to conclude local Hopf bifurcation here. And then this is perturbed by the small part of the spectrum and the small part of the matrix. But this is, in my opinion, not quite satisfactory, because what could happen is that very quickly several eigenvalues cross the imaginary axis. Okay, so I have a cluster of Hopf bifurcation points because I know nothing about the details how this crosses, and I will get a very small periodic oscillation which I never see. This is what I use global Hopf bifurcation language there, which was something I started out with when I was a student of Willi Jäger in Heidelberg. So this dates from 1985. I use a very old theorem on global Hopf bifurcation of mine, which settles this aspect. But that's a powerful technique, actually.
Okay, thank you very much.
Sorry for the long answer, but this was
you give a completely
very much to the point. I'm delighted about your
thank you.
perceptiveness.
So we will have another opportunity to understand the whole idea maybe next semester.
Well,
thank you.
It's your choice, you see. I mean, I can talk about lots of different papers and so on and say there's this and this and this and that, and then maybe you are interested in one or the other. Okay.
Yeah.
Another possibility is, of course, that I give a more specialized talk about some sort of technique, and then perhaps nobody is interested in that particular technique. But it is the choice is yours.
Yes, thank you. Okay, thank you.
I love to speak for you.
Thank you. So any other comments, questions? Just unmute your microphone and speak. Maybe now I have one. So you have a sensitivity for the what? For the you have a sensitivity, but you don't have a sensitivity for sine flux influence, right? You have last theorem for Nicola. Yes. No, not this one. Yes. Sine flux influence is not sensitive, but still, I think the sensitivity of sine flux influence is still very intuitive. I am suspecting maybe this is a non-generic phenomena. Maybe for generic reaction, this is still sensitive. Is that true?
Well, first of all, I should now Nico gave a counterexample. Okay.
Yes, Nico is here now. Nico is here.
Nico, where are you? Good morning. Where is he?
But maybe he's having breakfast. I'm not sure.
I am here, but I am in a dressing my daughter moment, so I'm listening from the other.
Oh, that's very nice. So yeah. So I will not answer that. Okay. Frankly, I'm not. I should be able to draw his example on this page. Okay. But I'm not. In my opinion, Nico, correct me while dressing your daughter.
No, I mean, for 1 second here. Hello.
So let me try to say something, and then, to my understanding, this is not a genericity question. This is an example where you look. I mean, if so. You have J star influencing J and J influencing J prime. Okay, let me try to draw this here at the risk of it break. So J star J influencing J prime, and then it should go from here to here. And I said, shouldn't this be obvious? I mean, if this an increase of J star increases the flow rate J. And if an increase of the flow rate J increases J prime, does that imply a plus here? And he says no. Now, no, in his case, I think it's a negative. You get a negative influence, right? In your example. Now, that is stable. If he gets a negative influence and you change everything slightly, these are all non-zero quantities. So it persists.
I see.
So this is an open, it's not a generic counterexample, but it's an open set of counterexamples.
I see.
Therefore, there is no hope to salvage that. Is it now, remind me, Nico, is it true that for some parameter regions you get a plus and for other parameter regions you get a minus?
It depends on the examples. It may be possible in the example, but there you can also have examples when you always have
the wrong.
Yes.
Yeah.
Always have.
Yeah.
Because you have other,
yes, that's what I said. I mean, what we are forgetting is that there's a J1, J2, J3. It's much more complicated than that.
Yeah.
Okay. And these may be plus or minus. We are not even talking about that. And then those may influence back.
I see.
J prime. And then it's a question of how all this balances. So I think, Nico's, sorry for misinterpreting your example, Nico, but I think this is the most striking demonstration that the transitivity question is not at all trivial.
Yes. Truly. Thank you. Yeah. Yes.
But it took me a very long time to figure out that there was this issue at all. Okay.
Thank you.
And perhaps this is related, if I may add this comment. So if you look at a diagram like that, you see that there are relatively few response patterns. Namely, you get a pattern where everybody's activated. Now, if you push any of these guys, everybody below will react.
Yeah.
So this is how we did this actually originally. We were plotting these flux influence matrices, big matrices. I think it's 40 sum by 40 sum in this case. And then I said, okay, in each column we have the corresponding fluxes going up and down, but we just plotted them by stars. Okay, I said, well, let me take off my glasses. Plus and minus I don't understand. Somebody else will come, some strong young mathematician who figures out the plus and minuses. But I see non-zero entries and zero entries. Why are there so few patterns? If you have, say, 48 columns, and you see only what? 1, 2, 3, maybe 4 with minor variations, 5 minor variations, 6 patterns. Why do you see only 6 column patterns in 48 columns? What is behind that? Why is the structure of response so relatively simple? It's not a random matrix. You see, if you put a random matrix, you get in 48 columns. Come on, there are so many, you have 48 bits, okay? Why should any 2 columns be the same or closely related? They shouldn't be. And that's how we intuitively started on this. But I should also say that Bernhard Brehm had an ingenious idea to actually derive this, because the theorem does not tell you what pattern you will see in a concrete example. You have to do calculations. And what my co-author Mochizuki on the first of these papers did, when we could only do monomolecular reactions, so many restrictions, this did not even fit the theory then. He actually calculated as symbolic expressions on a mainframe of Riken in Tokyo. He bought hours of computation time to get this sort of influence patterns. Okay. By completely symbolic computations, he computed all these polynomials. You see, there's an exponential term. You have to, in Cauchy-Binet, you have to go over the subsets of a set. And there are many, many subsets of a large set. 48, you have 25 element subsets of 48 elements. That's huge computations. And he got long polynomials and terrible storage, etc., etc. And what Bernhard Brehm did was he calculated modulo a prime number q. He said, let each RJM, let each partial derivative be an integer, mod a prime. And then I just calculate modulo q. I just calculate these determinants and matrices and so on, and inverses for a random integer, mod q. And if I get non-zero, it's non-zero with extremely high probability. So he used, if you want to calculate the zero of a polynomial, so you have a polynomial of m variables. And you are calculating in, say, z mod q. Let's see. Then you have no, a polynomial, I'm sorry, of degree m in n variables, of degree m in n variables. So the degree in our case is the number of metabolites, actually. Then the probability to hit a zero, a false zero by chance, to hit a zero of such a polynomial is m divided by the prime q that you study. So m was of the order 50 or so. And q, the prime that he uses, was of the order, it was 16-bit, so 2 to the 127, 2 to the 128. And if you divide 50 by 2 to the 128, that number is so small that it is much smaller than the probability of a manufacturing error in your computer processor, or even much smaller than the probability of a cosmic ray hitting your calculation right when you do it. And instead of working dozens of hours on a mainframe, he took milliseconds on an old laptop, which eventually got stolen anyway. So there are some Schwarz-Zippel lemma is the important thing to use here, and that's all in the paper. You find this on the
yeah.
So don't worry about the details. But I wanted to emphasize his very substantial contribution in both the transitivity proof and the actual realization here.
Thank you. Good. Any further comments, questions, remarks? Okay, if it is not the case, then let's thank our speaker, Professor Fiedler.
Thank you very much.
Thank you.
Thank you. Bye-bye.